I wish I did. I wish I would. I wish.
Usually at this time of the semester, I don't run any lectures anymore. Just let students working on projects. But here's different. We still have to do something.
Is it just me or is it dark?
You apparently I still hope to give you time to work on your project. We'll see. So what I'm doing here is in lab 10. If you see the lab 10 step-by-step instruction over here, I'm just reducing the difficulty level for you guys by either giving you the answer on my website or providing more solutions to the template. And I explain that in the class, so make it easier. So lab 10 is actually easier. Lab 10 is easier and fun. I just did it yesterday. Thank goodness we get a chance to do it. Thank you, Dr. Carlson. It's just so fun to play with. Let me show you. You gotta have some fun in order to be happy, in order to be productive, right?
Yeah.
Got depressed, you couldn't do anything.
That's what I'm saying.
You need to sleep well, you need to be happy, you need to be rich. How do you be rich? If you are rich, you're happy. Everything's done, right? Let's watch this demo first, so you know what lab 10 is requires you to do. Okay? It's called playback. You know what that means, right? You record a voice and play it back through a speaker. So I'm thinking probably I haven't get a chance to grade your proposal yet. But I think today's Friday. After the lecture, I'll have a lot of time to grade it. Hopefully by tonight, I'll give you the feedback. Hopefully I can finish it, the grading. If you haven't submitted, still do it. Okay, I'm not taking points off. It's getting delayed. I understand that. So I will still grade it, give you the feedback, give you the full point if you submit everything. And hopefully you guys will be ready to start working. Not you guys, but most of you guys will be able to start working on a project starting either during the weekend or next Monday, okay? So here you can still change your idea. Doesn't matter, I don't care. If you find out, oh, this playback experiment is so interesting and the code is provided, I probably can create a little music box for my kids 10 years from now. So he or she can play with it, okay? So for example, if you build a little music box with a PCB on it, have 2 buttons, right? You hold the button, you record your voice. When you're in college, right? 10 years later, you play it for kids, right? Whatever. I mean, it's another button you push, you play it back. Even though the quality of the sound is not really good, but it's still really fun to play with.
Like a Build-A-Bear?
Yeah.
Mm-hmm. Yeah, somewhere.
Like
Let's see.
we're gonna put
Must initialize the SPI
next
card.
Let's change this.
To record, Shift R, and press any key to record something. I'll do 2 demos for you, so you'll figure out why the first one doesn't work for the playback or back play. Okay.
Hello.
Playback, Shift key. So forward works and Shift B. So
Did you notice that?
playing back.
You can play it backwards. So which means you're taking the bytes from the bottom of the SD card. So it's gonna be totally, you see, hello, or right? You know what I mean? So it's really weird. So, but you couldn't tell if it's really playing back. So I think the best way to do it is don't speak anything. You could do either different tones. And I tried do, re, mi, but it's still not perfect because do you play back will be up, right? Even though it's a one tone. So I tried do, re, mi, it plays the tones, but plays back, still weird. So you can do this. Okay, so it's gonna play back perfectly. So let's try, so let's repeat that one so you know what I'm talking about, okay? So this is play forward.
So forward works and Shift B. So couldn't tell,
Right.
It's actually playing back.
Okay.
The only thing you can do is maybe just play a certain tone like do, re, mi, and then if it plays like mi, re, do, then you know it works. So let's try it. I'm gonna initialize it and then do a recording Shift R. Okay. Do, re, mi. Alright. So I'm gonna play Shift key. Okay, that works. Then shift B. Sounds weird, but basically you can tell the tone
that's
is
called
decreasing.
So do you have to flip
Okay,
each block?
so this is
Can you just read it backwards? Do you flip each block?
No, if it's difficult to flip since you don't know where that starts, right? So it's difficult to flip it because it's totally playing backwards with all the sample data from the ADC. So it's basically not making any sense. So me, right? Me becomes im. So things like that. So it's pretty fun to play with, I think. And so we are using the very similar technology or the technique that we introduced in Lam 9, which is called double buffering. So if we look at the assignments, you still have the paper with you, right? So as you look at here. Double buffering, let's see. I think it's at the bottom. Here. So the things when you are recording, the on-chip memory won't be able to record so many data points. So the registers are not able to hold so many data points, especially if you record for like over 30 seconds or something. So eventually, it has to be stored on the SD card. So the way to do that is, even though these are pretty small, but whenever this is sampling, you use a flag because this is sampling, and then you are sending the next one, sending the data, writing the blocks to the SD card. So you need flags. If it's being filled or not, right? If it's being filled, so see, you'll notice being filled. We are using this flag a lot. If this guy's being filled, okay, whenever it enters ISR to do the ADC, it's identifying this color and what's the color here? What's the color? Do we really have a color for the memory? Just a flag. Just name it color, right? You can name it whatever you want. We call it red and blue, but actually there's no difference. It's equivalent memory banks on the chip. You define a flag. For example, the current color is blue. The current color is blue. It's just color, right? So it's a byte variable. I call color right now is blue. It's like a state, right? So the color state right now is blue. Whenever it enters ISR, okay, if the color is blue and if, so it's AND logic, if the color is blue, if that one is being filled, which is another flag over here, the state of that memory bank, the buffer is being filled, has to be AND logic, okay? Being filled means it's not full yet, okay? Being filled. So ISR happens really quickly. Get into ISR every, 25 microseconds, for example. You get into ISR and check the two states. If it is red and the red buffer is being filled, okay, then do what? So it's basically the, remember, here, AD, this register holds the ADC converted data, right? This register is what? Is a higher byte of the 16 bits of the ADC data, right? However, we only have how many bits in the ADC data? How many bits? 10 bits. And we are using the left justified data, and we're only taking 8 bits of it. We're dropping the lower 2 bits because it's complicating things, which is okay. We don't need that kind of precise sampling. So we are dropping the lower, the ADRESH, ADRESL, whatever, there are 2 bits over there, we're dropping it. We're not using it, which is fine. So just keep in mind, in this lab, in the scope of this class, the ADC data is only 8 bits. It's being stored into this register. So it's already in there. It's already in there. You read it. So when color is red and when this is being filled, do what? Okay? it's being filled, right? It's being filled, which means that converted data, you want to put it into the red buffer. Okay? Make sense? Easy, right? It's making this easier for you guys so you can get time to work on projects. All right, so after the index hitting the limit, it's filled. It's filled. So next time you don't want to fill this anymore. It's not being filled anymore. It's filled. Okay, so it doesn't satisfy this entry anymore. So it's going to enter the next, which is over here. Okay? It's going to be what? Color is what? It's not red anymore. It's another one. Yeah, blue. Okay? It's blue color, but there's no color, right? It's just a flag. It's a state. Then it has to be being filled. Same thing. It's just directly copy. It's exactly the same piece of code for the blue buffer. So that's why I think lab 9 and lab 10 is really simple because it's repeating, just repeating itself. Okay? So this is the ISR part of it. So whenever it gets into ISR, it selects a certain buffer to fill, okay, depending on the current state of the buffer. So if you look at the diagram, so it's either filling this one or filling this one, okay? So the other one is not being filled. It gets back to the main block of the code and do what? For the one is not being filled, you get back to the main code, do another job, right? So what is that? What is the another job? So one is being filled. The other one is doing what? Sending that to the SD card, right? Okay, sending that. So it's filling this one and sends this one to the SD card, okay? And next time you alternate it. So the next time you're filling this one, and then you write whatever in here to the SD card.
Do we do this so that it takes less time?
No, it's because writing to SD card takes time. That's the first thing, and second, the on-chip registers, the buffers, they are not able to store a lot of data. So when it's getting sampled by 25 microseconds per sample, like 10 seconds will get a lot of data. You need SD card can go up to like 64 gigabytes, right? So in that case, you can do this alternately, and then eventually store a large amount of data to the SD card. Okay? The chip itself doesn't have a big memory on it, because memories are expensive. You need a specific foundry to fabricate that memory chip, but without putting the memory to integrate the memory with something else. You know what I mean? So you're doing a batch production for the memory itself. So you can just lower the cost of the SD card to $5 per block, right? But for the chips are pretty expensive. The silicon die is very expensive. And the memory takes a lot of space. So that's why we keep that most of the memory space outside of the chip. So these are only RAMs. You can have some non-volatile memories on the chip, but usually they are flash. For example, when we are uploading our code to the PIC, it does have flash on the chip. So eventually it stores the instructions, it's called instruction memory. But the thing is, it's probably only like a few hundred KB. Okay, not too much over there. For data memory, it's usually outside of the chip. We don't keep it on the chip or in the chip. All right, but for the registers, these are RAMs. These are volatile. After a part of those, they're gone. Data are gone. So, but flash memory, they can hold the data, but it's very expensive. Okay. So that's how we do the double buffering, and I think it's pretty straightforward for lab 9. All right, I think this week's task, I'm not expecting you guys have a lot of time to work on the project, but maybe just focus on lab 9, get it done. Okay, if you have questions, feel free to email me. I probably will send you the solution, some of the solutions. All right. Any question on lab 9 by far? Okay, just double buffering, right? And let's come back. Let's take a look at the in-class exercise from last time. Bonus points. We're at number 4, right? Do you have a copy? I'll let you turn it in. If we finish today's lecture, you don't have one?
I know.
Thank you.
Appreciate you.
Yeah. If we finish today's lecture early, I'll let you go earlier. Let's see. Number 4, I guess. You don't have one as well? Who else? Feel free to come and pick it up. Put a bunch over here.
Oh, I thought you were talking about question number 4.
What's that?
Can you go over page first? It's been a while.
First page.
The other side of
The other side of the page here.
yeah.
Let's see. Yeah.
Grab one for now too.
What about number 1?
The first one? Yeah, the first
Yeah.
line of code. Timer, right timer, minus 16.
Which one's better?
The first.
Oh, for this type of problem, it's a really simple answer, and test a lot of things, including the fundamentals of the timer writing. And so this will definitely on the final exam, right? Just keep in mind. I'll change a little bit things over here with the sign. As long as I understand what's really going on here, you should be able to answer that. Even though I transform it to a different format. Which one is better? This one is better. Which is better? The first one is better. The first line is better, right? I'm kidding. Which one's better?
Just don't write to the timer.
Bad joke. Which one's better? What you are trying to do here? Can anyone?
You're trying to take into account the time it takes to get an answer with the plus timer underscore timer, so the bottom one's better.
So eventually you want to plus this guy or minus this guy? Eventually.
Just draw it out.
The 1600 is the time you're going to be waiting, right? So you'd want to subtract
Yes.
the time that's already expired.
Draw it out.
Draw it. Yes.
That makes it.
Timer 0. Okay. What's the desired number of counts? Ideally.
1600.
Okay. Oh, it's over here. Desired. Given. Okay, given. We need it. We need this to be done. So it starts counting from here, right? Count towards that direction. If you start exactly from here, then it's perfect, right? However, what's the reality?
Thought your ISR takes time to actually do stuff.
Yeah, it takes time here, right?
Go.
How long is it? You need to record it at this time, at this point. How to record it?
The value.
This function is a really nice function you can directly use. It's called timer 0. Just read the timer, okay? Read the timer. As a function directly give you the time already spent since it enters the ISR. Where is that? Here or here? It's here. Right? How to do it? This is this guy. Because when it enters, it's already starting from here already, right? Oh no, it's already spent over here. So you don't want to stay. You don't want to start here anymore. You don't want to start here anymore because it's already spent that much. You want to start from here. You want to start from here. Right? Does that make sense? You need a copy? Yeah, it's over here. Just come over and pick it up. Oh, let's. you need a tool?
Yeah, I can go off.
Does that make sense? The timer is not started yet. Or it's already started, but the thing is, whenever you write this function, it's gonna reset it, right? It's gonna restart it from the point here. So this is the amount of time already spent and recorded by this function. So whenever you do this timer write function, it's gonna start from here, okay? So that's why you wanna directly add, that amount of time to here. So it's gonna start off a later time instead of here anymore because it's already spent. And you just need a certain amount of time for the ISR to make an accurate sampling rate.
So it's adding or it's subtracting?
It's adding, it's eventually adding, but you have to subtract it. If you put in parentheses, it has to be a subtraction in the middle because it's flipping.
Double subtract.
Yeah.
Essentially, you're subtracting by a
So it doesn't matter. So keep in mind, eventually, what's the conclusion? Eventually, you have to put a positive timer 0 read timer into the parentheses, no matter where you put it. But definitely not in the not in another nested parentheses, right?
Yeah.
Okay.
So this is accounting for the offset that occurs when it goes to the
Yes.
the go not done to start conversion and the setting a new sample to true.
Yes.
Okay, it just accounts for that time after.
Yes. Yep. That's right. Okay. Cool. Got it? Second one. The following code write 128 pages. What are written in the SD card's pages? What are written in the SD card's page? I'll give you a few minutes to look at it. Since your brain is not a compiler, right? Not mine as well. So take a look at it. What's the block size? What's the block size? 512 bytes. Keep in mind, important stuff to be tested in the exam. Okay, 512 bytes. It's a constant. We're not changing that. For SD cards, it's always 512 bytes. There might be other block sizes for other memory cells being sold by Samsung or someone else, Micron, but for the Kingston, right? It's the name, brand of the SD card. It's always 512 bytes per page or block. Same term, page, block. 512 bytes per page. So that's the block size variable or constant. And I'm writing 128 pages. So totally how many bytes?
128 times 512.
128 times 512, right? Because every page has 512 bytes. So another question to ask you guys for the address. Do you need an address for a byte or do you need an address for every single bit?
Address for a byte?
Hmm?
Address for a byte.
Address for a byte, okay? So for example, this is the initial address. So what's the address of the last byte of the page?
127. Because address 0 would be the first.
Yeah, that's address 0, right? So the bottom byte has the address of this.
11. Yeah.
Okay?
Okay.
So what's the initial, if there's another page after it, right? So stacked together. So what's the address here?
0.
No,
Oh,
it's
512.
adding.
Oh,
Yeah, it's 512.
Yeah, that makes sense.
0 come back, right?
Mm-hmm.
Digital circuits is not that smart. Only recognize the address. So the address here will be 512.
Yeah.
Okay? Make sense? Okay. All right. So this guy has a block count. So block count means how many blocks, how many pages. Okay? Block size means how many bytes. It's 512 bytes in each block. And by how many blocks. So if you have this nested for loop, what is this guy really doing? Look at this line.
Block by
Block by block and byte by byte, right? Eventually you want to access every single byte in all the blocks.
Yeah.
So it's basically doing what? It's writing into every single byte for all the blocks. There are 128 blocks and 512 bytes per block, right? It's trying to access every single one, every single byte in there. See? Nested for loop, right? Whenever you got a block zero, right? And get into this for loop and write 512 bytes into it and then comes back for block one. Then write another 512 bytes, come back for block two. Keep going until block 127, right? So totally it's writing into 128 blocks and 512 bytes per block. So what's the what is this constant number here?
512.
512. 128. So every time it enters the byte, it's writing something into that buffer. Okay, it's just a memory storage. Anyway, so the sample here is the index. So it's writing every time it enters it, it writes into it. Okay, it writes into it. Oh, that's another thing to talk about. So what's going on? I mean, it's confusing people, right? I mean, you're talking about blocks and pages for the SD card. Why you are getting a on-chip memory buffer here engaged? What you are doing?
Well, you can only write to the SD card one block at a time, right? So you need to write everything into a block and then send it over to the SD
Yes.
card.
Where did you send it over?
With the SD card write block.
Yes.
So wait, is the process essentially it gets the thing, it loads the buffer with like the whole block, then it writes the block, and
Yes.
it does the next one, and
Yes.
it loads it, puts it in, and
That's right. So see, every time you do this for loop, the semicolon is over here. So which means this secondary for loop will be finished first, which is getting 512 bytes in there. And eventually the 512 bytes is not too big, right? Just 512 bytes. Your on-chip buffer can handle that. So eventually this buffer handles that 512 bytes, and eventually after the for loop, you see the semicolons over here as the one-liner for loop. So it's gonna do it for 512 times, and eventually when it's done, come back, directly move to the next, which is write block. So write block is only writing 512 bytes, keep in mind. The SD card is writing and reading by 512 bytes.
So the line after the for loop saying block counts what we're storing, so we're just putting in like
This.
Where's block counts? Where?
it says red buffer sample equals block count.
Yeah, yeah.
So each page is just going to be like 00000
Yeah.
for block 0.
Yes.
Next page is 1111.
Yeah.
So in every
Yeah.
page you're just writing what
Page
you're
number.
on.
Yeah, every page is writing a page number into that page. A lot of information, right? Super valuable information. So let people know the page number, right? Okay. So what about next? After this is written, it takes time, right? Let's check the status. This is nothing to modify. This is already designed by the PIC, whoever, microchips, computer science people, right? Who designed the compiler. So you just have to wait here until it's complete. So whenever it's not complete, just wait. Whenever it completes, move to the next, print it out, okay? Print it out. And increment what? This is what we are talking about over here. So every time, so it's writing in here, right? Writing here. But the address is not changing. It's writing into it, but the address pointer is not incrementing. Or it's coming back. I don't know the details of the digital designer's strategy, but eventually this original address is not changing. So that's the point that it enters the beginning of the bytes of the block. So which means at the very beginning, it's writing into the original address is on the top. It's on the top of the page, the very first address. So starting from the first, you write into it, so it's writing a whole 512 bytes into the page, okay? But that address is not changing, even though it writes into the whole page. But the initial address, this variable is not changing. So next time you want to start another page, okay? So the starting address is also on the top of the second page. But that address has to be changed in order to write into that page.
When we write into it, we use
Okay?
this.
So what is that address? Should be the second page. What's the page 2's first data point's address? The original address plus the block size, right?
Yeah.
Which is 512. See here? 512 is the address of the second page on the top. So you increment that address for the second page and you do it again. So until you finish all the 128 pages. So it's all written into the pages of the blocks, or written in all the blocks. Same thing, pages, blocks, same stuff, right? Any question on this? Okay, next.
Wait, really quick, so at the end of the day, is it block by block then?
Yes, it's block by block, yeah, because it's doing, see here? The buffer, this buffer, the whole thing is 512 bytes. Because this for loop is doing 512 times.
Yeah.
Eventually this one holds 512 bytes. It's an array. So for the write function, it directly throws this whole thing in it, starting from this starting address. So that's why it's throwing the whole block to the SD card every time. So embedded system engineers, we don't really care about the digital details of the protocol. So this writing function, eventually there are a lot of things, nitty-gritties of the protocol, on and off, all the timing for SPI, right? We don't worry about that. So that's it's right at the bottom level of design for embedded engineers, I think. So do digital design engineers or verifications have to handle the Verilog, RTLs, those kind of things. All right, let's move to the next. So this is a new structure in Lab 9. It's called a structure data type. Structure. Structure. So structure, this is structure's name, and these are structure's numbers, members. These are members. That's a structure.
What were we using before the tech def enum? Is that? Well, I
Mm.
thought that was a struct.
It's also struct, yes. But these are states, right? They're just the constants, I think. These are also constants. Yeah, these are variables.
Okay.
Actually, no big difference. It's just like trying to give a. No, it's a number. It's enum, I think. Not a struct. So the struct means you can access the member by doing, I think it's asking you here, right? What are the two members of the write buffer structure variable? What are the two members? Let me know.
My buffer state and
Yeah.
buffer.
Yeah, state and also the data itself, right?
Yeah.
So how do you access the members? So that's what, use a dot.
Oh,
What's-
so
what-
it's like basically kind of a mini version of a class.
Yes.
you see.
Yeah.
But like instead of using functions, it's just kind of like to hold data and stuff.
Yes, yeah. In class you can have functions, you can have methods, right? Methods and other things in there. But this is structure, and you can have members in there. So if you do this, see, I initialize it over here. So you can do a red buffer dot, right? Dot. State. So you can access this member here. Okay? And that's why you can see here, write buffer dot buffer. So you can access the data, the buffer itself, by doing this structures data type. Yeah, just data type, nothing else. No magic here.
It's magical.
Have been enjoying the bonus points by far? Going out of control a little bit. So, yeah, that's okay. Yeah. One more thing. So in the future, these will be like 1 point and 5 points. So you guys are not getting like 1,000 out of 100, right? In future. One more thing. So for the percentage of all the assignments, so in the future, you can see right now I'm still using 70% for the assignments and labs. but it's reading the syllabus, and also I communicate with students as well. So it's going to be 60%. So eventually you'll see it will be lower eventually. But still good, right? Still not hurting anything. This is not hurting anything. But will be a little bit lower in the future eventually. Since it's not 70%, it should be 60%. Final exam and exam 1, each of them is taking 10%. So eventually the 2 exams are taking 20%. Project is also 20%. So spend a bit more time on projects. So I'm giving you a lot of solutions to the labs, lab 9, lab 10. Lab 14, there's no coding. It's basically just it's given. Soldering and also the hex file is given. It's just directly download the hex file and just look observing, right? Get a coffee and observing. Look at the curves. Right? Easy. So eventually, project 20%, 2 exams 20%, all the rest 60%. Okay. We'll see. We'll see how that goes. It's close to Christmas, right? It's a Christmas gift for you guys.
Thank you, Professor.
You guys are like, I don't need drop a lab anymore, because drop a lab. Oh, anyway, it's okay. It's not helping. Anyway, I want 120. I don't want 100.
Give me the 120.
Drop a lab, give me 100. But doing bonus points, give me 120. What is this?
You have to read the data, print it, yeah.
Oh, 2 steps. 2 steps.
Yeah.
So reading and writing are both taking 512 bytes, right?
Yeah.
So reading the entire block, 512 by 512. And then when you're incrementing the address, you increment by 512.
Yeah.
Make sense? Okay. Next. Oh, that's a double buffering. Double buffering. What is it? Assign the ADC value to where? Oh, that's easy. You guys are just working on it, right?
Oh.
Yeah.
Alright.
Oh, just
I'm
do it.
writing
Just
down
do it.
the
Just do it.
forward. Yeah, we're writing down the forward.
Yeah. Just do it. Because you know this wait. You can find out the member here, right? What's the member holding the data? It's a red something dot something, right? Dot no, it's here. Red buffer dot buffer, right? So that's the data holding, right? So you wanna do something. Eventually, this is the red buffer being filled, and this will be the blue buffer being filled. I just give you some time to work on it. We have 9 minutes left. So when you are done, turn it in. I'll grade it after class, and log the bonus points this evening, so I don't have to do it during the weekends. Whoever not getting back your paper from last time yet, I know some of you. Understood?
We want to do this.
You let me know, guys, you don't have it.
Gets to 512, right? Or there 512 page 2.
Do the size.